Hello and welcome, class, where we are finally going to be building molecules. So as we leave chapter 4 and enter chapter 5, we are going to use the characteristics of atoms that we have discussed based off of the valence electron count to start building compounds. We're going to start building molecules. So the way that chapter 5 is broken down is we are going to be talking about ionic compounds first. After this, so in part 2, we're going to be talking about molecular compounds. And then in part 3, we're going to be talking about some experimental methods that are used to determine what the formulas are for ionic and molecular compounds. So basically the end of the chapter is going to be, how do we know? But we're going to be talking language, nomenclature, how we build compounds, what we call compounds. That's what we're going to be talking about first. So let's just get into it. All right, well, in order to build a molecule, we must talk or revisit like what drives atoms to come together. So each atom strives to achieve a noble gas electron configuration. And this we've talked about before. Notably, we talked about this when introducing what the ionic charges were on certain elements, and either the atoms would gain electrons or lose electrons in order to achieve this noble gas electron configuration. Well, sometimes an atom can't just freely gain or lose electrons. Like, what if there aren't any electrons around, or what if it doesn't have the energy to lose them? Well, it's going to be more of a common occurrence that an atom is going to find another atom as opposed to just finding a free floating electron. So our main group elements, again, those in the S and P blocks, strive for our 8 valence electrons, and they're going to gain the noble gas configuration by either gaining or losing electrons and forming ions in the process, again by 2 atoms coming together. One more than likely is going to want to lose electrons, one is going to want to pick up those electrons. If, however, both atoms want electrons, the 2 are going to have to compromise, and they're going to end up, quote unquote, sharing their electrons. In part 2, I'll explain in more detail why I have share in quotes here, but for now, just kind of bear with that idea. Either our atoms are going to completely gain or lose electrons as one thing transfers to the other, or the atoms are going to compromise and they're going to share. If the atoms are sharing electrons, then this is what builds molecules as opposed to ionic compounds. Now, why 8 valence electrons? Why do we strive for that noble gas configuration? We strive for 8 valence electrons, kind of based off of this illustration of the cup here. Now we can imagine this cup is the, let's see, I'm gonna write this sideways, valence shell of our atom. And the valence shell contains an s orbital and 3 p orbitals, right? There's an s and 3p, not 3 as an energy level, but 3 as in there are 3 p orbitals in any main group element. And if we reach a noble gas electron configuration, that's going to mean that this single s and all 3 of these p orbitals are going to be completely filled with electrons. It's like we're filling up this glass with milk. We can see in this hypothetical example, this particular atom, right, represented by this glass of milk, has 2, 4, 6 electrons in the valence shell already, and it needs 2 more if it's going to have a completely full valence shell and a noble gas electron configuration. Now, it just so happens that in order to get that noble gas configuration, we're going to need 2, 4, 6, 8 electrons to do it, again, if we're working with a main group element. So this explains our octet rule and why it's most commonly 8 valence electrons that is going to stabilize our atom. Now, there are some exceptions to this. Some notable exceptions are the transition metals, as well as the like lanthanides and the actinides. These are groups on the periodic table that break the octet rule. These are elements that don't strive for solely 8 valence electrons, and the reason why and like what rules they follow get explained in higher level chemistry courses. So organic chemistry, inorganic chemistry, P-Chem, and we're gonna leave the conversation for later. We're gonna put a pin in it because it's sadly just beyond the scope of this class. Another exception though that we can explain, we can see listed down below, hydrogen and helium only strive for 2 valence electrons. They only strive for a duet instead of an octet. And this one is easier to explain since hydrogen and helium are both only filling their lowest lying orbital, that 1s orbital, and once this is filled, they're going to be satisfied. They have too few protons to keep adding electrons on top of this. So hydrogen has 1 valence electron, helium, also with the 1s shell, has 2 valence electrons, and this is going to be enough for them. So they're only going to need 2 valence electrons, and then they are satisfied. Okay, so let's talk about ionic compounds and how they help to satisfy particular elements' octets. Namely, ionic compounds form by the combination of a metal and a non-metal. Now, the reason why ionic compounds almost exclusively form when a metal and a non-metal come together is because metals are very good at giving up their electrons. They have very low ionization energies. Right, we talked about this back in chapter 4 when we were talking about periodic trends, ionic trends, and in that same vein, nonmetals have very high electron affinities, so they want the electrons, right? Nonmetals are very good at taking electrons because of that high electron affinity. So if we're combining 2 things together, a metal like sodium, where we can see its electron configuration is provided down below, we have 1 single valence electron. And if we're partnering that with a nonmetal like chlorine, where its electron configuration is also provided below, and we can see that it has 7 valence electrons, well, sodium is going to want to reach its octet by getting rid of this 1 electron, and chlorine, on the opposite side of things, wants 1 additional electron in order to reach its octet, right? In order to fill its valence shell, where it currently has 7, 8 is so close. All we need to do is take the 1 electron away from sodium, which is being illustrated here. Our electron is leaving sodium, and it's going to hop right on over to chlorine, which is what is also being illustrated up on top. The electron is going to be leaving sodium's valence shell. It will be moving into chlorine's valence shell, and this is going to give sodium an electron configuration of neon, and it's going to give chlorine an electron configuration of argon. So we have 2 nice closed-off noble gas electron configurations. Sodium is going to have a +1 charge because it has lost an electron. Chlorine is going to have a -1 charge because it's gained an electron, but when you put these 2 things together in a compound, what we end up with is something that is charge neutral, right? This +1 and this -1 are going to cancel each other out, meaning that we have no charge across the entire compound so long as we have equal parts sodium and chlorine. So this is how ionic compounds form, and every future ionic compound we're going to be working with and describing, explaining, observing, etc., are formed by a similar process. Our cation, which is caused by the metal losing electrons, is going to bind to an anion, which is formed by a nonmetal taking electrons. So the bond that is holding that positive and negative together is what we call an ionic bond. Now we can further describe this with the description that we have below, right? The definition that we have below. An ionic bond is a type of an electrostatic attraction between a cation that has a positive charge and an anion that has a negative charge. What does electrostatic mean? Electrostatic is the fancy scientific word for the phenomenon that we have been observing since childhood. Positives and negatives attract. That is what electrostatics has to do with. It has to do with the interactions caused by the positive and the negative charges. So an electrostatic attraction is the attraction that is caused by positives and negatives coming together. An electrostatic repulsion is caused when positives and positives come together, or when negatives and negatives come together. But if we're looking at an ionic bond, which is by definition an attractive phenomenon, we're going to be partnering together the positives and the negatives, aka the cations and the anions. Now, so long as we have a cation or an anion sitting around, they are going to lump together. When I say that, I mean an ionic bond is not strictly one bond between a sodium with a plus charge and a chloride with a minus charge, which is what we can see here, but rather if there were another Cl- nearby, it's going to stick right here on the sodium. And if there's another Na+ nearby, it's going to stick right here on this chloride. And if there was another chloride nearby, etc. Like, we're going, as long as there are positives and negatives sitting around, as long as there are still more ions in the pile, they will slowly build together into what we call a quote-unquote infinite crystal lattice. Now, we say infinite because it could, in theory, just keep forming so long as we had more Cl-, so long as we had some more Na+, we could continue building off of this crystal. But once we run out, right, if we are thinking realistically, there is going to be a point where we run out of material, and that is going to cease the formation of our crystal. So we can see that this salt crystal here, this combination of Na+ and Cl- is forming this really awesome cubic shape. If you ever have the time, right, and if you're curious, you can look at a piece of salt, like a little grain of salt, and it will also have a cubic kind of structure. And we can trace that cubic structure at the macroscopic scale all the way down to the molecular scale. Even if we look at the combinations of individual ions, we are going to see where that cube comes from. It's because sodium and chloride are very stable, forming these alternate positive, negative patterns across the entire crystal. And it just so happens as you build that up in 3 dimensions, you get something that looks like a cube. So that's pretty cool. All right, so if our ionic crystal can be infinite, right, if it can be any size, just so long as we have the materials to build it, how do we then, in a really nice and concise way, represent what type of ion compound we're working with? Well, for this, we have to revisit our definition for chemical formula, but also introduce a new definition known as the empirical formula. All right, so just as a reminder, a chemical formula is a combination of elemental symbols and numeric subscripts that are going to represent the composition of our substance. The last time we talked about this was way back in chapter 1 when we were first introducing the definition of a compound. All right, so now that we are actually building compounds for ourselves, it's going to be really important to kind of revisit the definition of a chemical formula. So a chemical formula, we can see an example down below. We have a combination of elemental symbols here. We have magnesium and chloride, as well as numeric subscripts. We have a 21 and a 42. And there are a couple of other examples we have listed down below. All right, so if this is, again, kind of revisiting the definition of a chemical formula, what does that make an empirical formula? How is this special from a chemical formula? Well, an empirical formula is a form of a chemical formula where specifically the numeric subscripts have been reduced to the smallest whole numbered ratio. So we just reduce the subscripts down to the lowest form that they can possibly show. And the reason why we do this is the empirical formula is meant to be kind of a catch-all to represent our quote-unquote infinite ionic crystals that are held together by any number of ionic bonds. We are totally fair to use empirical formulas as ionic formulas, or rather in substitution for ionic formulas, because if we kind of observe these 3 formulae down below, each of these 3 are meant to represent a magnesium chloride crystal, just of varying sizes. Well, it turns out that if you have a magnesium chloride crystal that is comprised of 21 magnesiums and 42 chlorides, versus if you, like observe the properties of this, how easily it dissolves, how reactive it is with other compounds. If you compare all of those observations to that of a magnesium chloride crystal that is twice the size, so we have 44 magnesiums and 88 chlorides, or not exactly twice, but roughly double the size, what we end up with is the exact same set of observations. Both of these have the exact same chemical and physical properties. It just so happens that one of these chunks, is twice as large, or approximately twice as large. So if these two materials behave in the exact same way, then the chemical formulas we use to represent them should also be the same. Right, a chemical formula is not just a representation of like what physically is sitting in front of you, but what is chemically unique of the thing sitting in front of you. So if our chunks of matter behave in the exact same way, they should have the same chemical formula. So this is where it pays to reduce our subscripts down. Let's see, eraser. So we're going to observe our subscripts. We're just going to reduce them down by the lowest whole numbered, or to the lowest whole numbered ratio, and that's where we get our MgCl on the other side. So how we get this is we observe our subscripts that are present, and we are going to divide each by the lowest within any one formula. So magnesium 21, chlorine 42, if we reduce each of these by the ratio 21, right, because we're just looking at counting numbers, we can scale up, we can scale down, so long as we are observing what the ratio is between magnesium and chloride, or chlorine, which ends up being a 1 to 2, and we can see that by reducing our subscripts here down, or with the magnesium 44, chlorine 88, similarly here, we're going to reduce down by the lesser to create a nice whole numbered ratio, a sizably small whole numbered ratio. We can see that we have 1 magnesium for every 2 chlorines, which is exactly what the empirical formula ends up being for both of these two compounds, both of these two chunks of stuff. So whether we're looking at 21 magnesiums and 42 chlorines, or if we're looking at 44 magnesiums and 88 chlorines, one chunk of matter is twice as big, both have the same set of physical and chemical properties, so we can reduce their chemical formula down to the empirical formula and use this to represent both of those chunks of matter, since both of them have a 1 to 2 magnesium to chloride ratio. Okay, so now that we've introduced what the empirical formula is, we are going to use the empirical formula to represent our ionic compounds, regardless of what ionic compound we're working with. If we're looking at a combination of a metal and non-metal in some type of compound, we are going to use our rules here to write out the ionic formula, aka the empirical formula. All right, so we're going to follow these 2 steps here to write our ionic or empirical formula for the ionic compound we are working with. First, we have to determine what the stable charges are on the cation and the anion if they are not explicitly given to us. And the reason why we need to know what the stable charges are is if we look at step 2, once we know what the charges on the cations and anions are, we can use them to figure out how many are necessary to make a charge-neutral compound. This is the key that we are going to need to adhere to when writing our ionic formulas. We need to make sure that all of the positives and the negatives cancel out. The reason why we want to ensure this is when we observe matter out in the wild, it matter naturally strives to have charge neutrality. It's very unstable just to find a single positive charge or a single negative charge kind of out there in the wild. So we want to make sure that our chemical formulas are going to adhere to what we physically observe the natural behavior of matter to be. All right, so let's work together and determine the empirical formula for the compound lithium oxide. So lithium oxide we can observe as a combination of a metal, since lithium is on the left-hand side of the periodic table, and oxide, We're going to talk about where this name kind of comes from, but it is in reference to oxygen, which is a nonmetal on the right-hand side of the periodic table. So since we have a metal and a nonmetal, this is how we know, aside from, you know, the context of we're talking about writing ionic formulas, but if you didn't have this context, if you see a metal and a nonmetal, this is how you know you are working with something that is ionic. All right, so step one, we have to determine what the stable charges of the cation and the anion are, since they're not explicitly given to us, like we're not told what the charge of lithium is or what the charge on this oxygen is. So how we figure this out is observe the periodic table and write out the neutral ionic electron configuration for our species. This is going to tell us what the most likely ionic charge is going to be once it reaches a stable noble gas configuration. So lithium's neutral, right, this is neutral lithium's electron configuration. We have a core of helium and a 2s1 on top of it. And oxygen's neutral electron configuration is a helium core, 2s2, and 2p4 on top of that. Doing this over here. All right, so we can pretty easily see that lithium wants to lose a single electron. Right, if we're striving to have 8 valence electrons, lithium would have to gain 7 in order to reach an octet, or lose 1. And losing 1 is that path of least resistance, so we're going to lose this 1 single electron, meaning that our stable lithium charge is going to be lithium with a single +1. Now oxygen is either going to have to lose all 6 of these electrons, or it's going to follow its non-metallic behavior with a high electron affinity, and it will gain 2 electrons in order to meet a total of 8. So if we add 2 electrons to our oxygen, this is going to give us a new electron configuration that is equivalent to a core of neon. So in doing so, we've given, or in creating our ions, we now have a lithium that has a noble gas configuration equal to helium, and oxygen has a noble gas configuration equal to neon. Since our oxygen gained 2 electrons, this also means that our oxygen is going to have a 2- charge. All right, so we have a lithium with a single plus, we have oxygen with a 2-. We're gonna start putting these things together. Now again, rule number 2 says that we're going to need to combine a certain number of cations and anions to reach a charge-neutral compound. So the numbers of positives, when we start combining these together with our negatives, are going to have to cancel each other out. So if we have a single lithium and a single oxygen, we can see that we have a single positive and 2 negatives. This means that when combining the single positive and the 2 negatives, we're still going to be left over with 1 negative charge, right? +1 minus 2 gives us a -1, which is not charge neutral. What this tells us is that we're actually going to need a second lithium with another positive charge. This is going to give us a total of +2, which is going to cancel out that -2 from the oxygen. Now we do have something with a 0 total charge and something that is, as a result, charge neutral. So we're taking 2 lithiums and putting them together with our single oxygen with a -2 charge. And when doing so, the chemical formula that's going to represent this combination is a lithium with a subscript of a 2, since we have 2 of them, and an oxygen for that single oxygen that we have. Li2O is the chemical formula that represents a lithium oxide crystal. Regardless of how many lithiums with a plus charge and oxygen with a minus charge that might be there, we can assuredly know that if our compound is charge neutral, no matter the size of the crystal, it's always going to be 2 parts lithium, 1 part oxygen. So on the other hand, if we're given an ionic formula and we're asked what it's named, how can we figure this out? Well, there are 2 different sets of rules. The first set of rules we're going to look at corresponds to when our cation is a main-bodied metal. Now, for a simple kind of definition, the main-bodied metals that are going to be following the set of rules we're talking about here are the S-block metals. The P-block metals can sometimes be a little bit more nuanced, so we'll talk about those in the second set of rules in a little bit. So for here, we're just focusing on S-block main-bodied metals. Now, if you're given the chemical formula, like for instance, MgCl2 down below, we're returning to this MgCl2, the cation, we're going to call it whatever the elemental name is. So if we observe the periodic table and we find Mg on the periodic table, we know that this corresponds to the element of magnesium. The anion, which is this Cl, right, this nonmetal that has allegedly gained some number of electrons, it has gained a negative charge, we're going to refer to it by the elemental name minus its suffix, and we are going to add IDE. So this element is known as chlorine. We are going to drop the suffix, so we're going to get rid of that INE, and we are going to add IDE. So the new name for this anion in the ionic compound is chloride. The importance of taking your anion and changing its name, of removing its suffix and adding IDE, has a lot of symbolic meaning to it. What it's really meant to symbolize is that the combination of magnesium and chlorine has resulted in a new compound. That it's not just a physical mixture of magnesium and chlorine, but now they have chemically bonded together, creating one new thing, magnesium chloride. So this IDE suffix is really meant to symbolize that we have a chemical bond here, we have an ionic bond between the magnesium and the chlorines, creating some new compound. All right, well, the second set of rules then occur when our metal predominantly is a transition metal. In addition to the transition metals, we follow this set of rules if we are also paying attention to a heavy metal. And a heavy metal that is not a type of transition metal or that is not on the F block is a P block metal. So these are going to be metals like lead or bismuth or tin. These are metals that have a pretty hefty number of protons and neutrons. They're literally heavy elements on the periodic table, and these heavy metals are going to follow the following set of rules because these are also elements that can exist with multiple possible ionic charges. So we've talked about the example of iron already, how iron can have a +2 charge, it could have a +3 charge, and both of which are stable. Heavy metals like lead, bismuth, tin, etc., that are in the P block also can have multiple stable charges. So this is why they follow this latter set of rules. In the latter set of rules, the cation, which is your metal, you are still going to write out what the elemental name is, but you're also going to have to add a piece. Because each of these metals that exist as transition metals or heavy metals can have multiple stable charges, we're going to have to add some acknowledgement for what the charge on that particular metal is in this compound. Because if you don't, the chemical formula could signify, or the name could signify, a number of different possibilities, a number of possible outcomes. So you have to be really explicitly clear as to what the charge on your cation is, since it could vary. The rule for the anion, though, is the exact same as previously. So we're going to take the element, we're going to subtract out the suffix of the elemental name, and we're going to add IDE to symbolize linguistically that we have a chemical bond between the cation and the anion element. All right, so let's observe the chemical formula for Fe2O3, aka rust. We are going to write out the proper chemical name, the proper standardized name for rust using the chemical formula. All right, so our first step, since we need to know what the ionic charge on our cation is, according to our naming convention for the cation, let's kind of break down the ions here and figure out what the charge on this iron is. Since if we were just to start with the electron configuration, there are multiple possible outcomes. What we're going to do instead is look at the oxygen that's present here. Now, oxygen always makes a -2 charge, right? And we just observed why when working with the lithium oxide example. If we go backwards, our lithium oxide example contained our breakdown for oxygen, why it gains 2 electrons, and there's really no alternative in this case. Like if you're working with oxygen as an anion, it is going to gain 2 electrons always. This means that our oxygen is always going to have a -2 charge if it is present in some type of ionic compound. So if we take this information and move forward, we know that our oxygen inside of this ionic compound assuredly is also going to have a -2 charge. Now, since there are 3 oxygens present, this means that all of the negative charges being summed together create a total of a -6 charge. Since this chemical formula is charge neutral, this means that the combination of our ions are going to have to balance out all of these -6 charges. This is going to give us a total of a +6. Since there are 2 ions present, we're going to split this charge between the 2 ions, meaning that each individual ion is going to have a +3 charge. So even though iron, if we were to start with the electron configuration, it would give us either a +2 or a +3 outcome. If we observe the ionic formula itself, because oxygen always has the same negative charge, we can use it to assuredly figure out what the specific charge is on the iron in this specific context. So the iron has to have a +3 charge, which narrows down the options for the electron configuration of this iron as well to the +3 option. All right, so now that we know what the charge on our iron is, it's a +3, we can actually get to naming the compound. The name of the compound then, if we start with the cation, we're gonna begin with the element name itself, iron, and we're going to add a Roman numeral to identify the charge. Since iron has a +3 charge in this case, we're going to add a Roman numeral of 3. Right, so the 3 present here signifies, if we were to go in the reverse direction, we know exactly what the charge on the iron is. We don't have to guess using the electron configuration. We don't have to pay attention to the oxygen. We don't have to do any extra work. We have already explicitly laid out the work. With this Roman numeral, we know that the iron has a +3 charge. All right, from the cation then, we move on to naming the anion. We're gonna write out the elemental name oxygen. We are going to drop the suffix, we're going to drop the whole -gen, and we are going to add IDE. This in combination then, if we were to clean up this word, becomes oxide. So the combined name of Fe2O3 is iron 3 oxide. Iron 3 oxide. All right, so we have actually come to the end of part 1. We've talked about what it means to be an ionic compound, what it means to have an ionic bond, and how we go about either writing out chemical formula for ionic compounds or writing out the names provided a formula. So I would like you guys to take a breather, see if you can't write down the formula or name for each of these following 5 ionic compounds. All right, so let's come back together and write out the either names or formulas for these ionic compounds. So if we're starting with SrBr2, I need to really make sure I don't just accidentally say the name. If we're starting with SrBr2, we can see that the metal here is an S-block metal, which means we're following the main block metal rule. We're just gonna write out the cation's name, which is strontium. And the anion, we're going to write out its name, we're going to drop the suffix and add IDE, which turns the name bromine into bromide. So the name for this ionic formula is strontium bromide. All right, next we have beryllium nitride. Because we are not told explicitly what the charges on these ions are, we're going to have to look at their electron configurations and figure it out. So beryllium, where it is on the periodic table, let's see, I'll write it right down here, has an electron configuration of He 2s2, and our nitrogen has an electron configuration of He 2s2 2p3. All right, so the beryllium, it's going to be easiest for it to gain a charge, to gain its noble gas configuration. If we just lose these 2s2 electrons, that's going to give a 2+ charge to the beryllium. And our nitrogen has a total of 5 valence electrons. Since it's over halfway to gaining, or over halfway to a total of 8, it's going to be easier for it to just gain 3 electrons. These 3 electrons are going to come from the berylliums. As they begin losing electrons, the nitrogen will pick them all up. Each individual nitrogen, though, is going to be the most stable if it has a 3- charge. In doing so, our beryllium will be left with a helium core configuration, and our nitrogen will be left with a neon core configuration. Now that we know what the charge on the beryllium and the nitrogens are, though, we're going to have to put an equal, or not an equal number, an appropriate number of the ions together to make sure that our compound is charge neutral. So a beryllium with a 2+ charge at first is just going to be partnered with a single nitrogen with a 3- charge. We can see that we have too many negative charges, right? We are not charged balance. So we're going to have to add another beryllium with a 2+ charge. Well, this brings our total positive charges, total number of positive charges, up to a +4, meaning that we have too many positive charges now. So we're going to have to add a single additional nitrogen with a -3. And it would appear at this point that our charges are still not balanced. We are at beryllium with a total of a 4+, nitrogen with a total of a 6-. So we're just going to add another beryllium. Now we have a total of 6 positive charges across all of our berylliums, 6 negative charges across all of our nitrogens. And if we were to put all of this together, we would be left with beryllium 3, since there are 3 berylliums present here, nitrogen 2. Be3N2. All right, aluminum iodide, we can follow a similar approach. I will leave the electron configuration determination up to the viewer, but our aluminum is the most stable with a +3 charge, and our iodide is the most stable with a -1 charge. So cations, you notice, tend to be listed first, and the anion tends to be listed second. And this is true in nearly every ionic compound that I can think of, especially at the general chemistry level. So our aluminum has a +3, iodide has a -1, meaning that we're going to put 1 aluminum together with 3 separate iodides. This is going to make sure that we have a total of a -3 charge to balance out all 3 of those positives coming from the aluminum. All right, we're in the home stretch, our last 2, SnS2. If we want to name this, compound, first and foremost, tin is a heavy metal, meaning that it actually has multiple possible ionic charges. Because it's a heavy metal, we're going to have to follow the second set of rules for naming this species. We're going to have to know what its charge is in order to name it appropriately. Well, sulfur is an element, much like oxygen, that is going to have a consistent ionic charge, a consistent anionic charge. Each sulfur is the most stable with a -2 charge. And there are 2 of them present inside of this compound. So there's a total of a -4 charge that the cations in combination are going to have to balance out. We can see that we only have 1 cation present, though. It's not SN2, it's not SN3, it's just a single SN, which means this tin is going to have a +4 charge in order to balance out all of the negative charge that's coming from the sulfur. So now that we know what the charge on our tin is, we can name this compound. It is a tin 4, right? Because again, we have to write the charge in Roman numerals here according to our naming convention. Our tin 4 is going to be the cation, and the anion is going to be sulfide, right? Because again, sulfur, we drop the suffix, we add an IDE. Last but not least, we are working or charged with naming tin 2 oxide. Here exactly we can see an example of two stable charges on tin. The first has a +4 charge, the second has a +2 charge. So if we take our tin with a +2 charge, combine it with an oxygen, that, again, we have seen a couple of examples now. Oxygen is the most stable in its ionic form if it has a -2 charge. These two things, when partnered together, are going to create charge balance. And this is going to mean that the chemical formula for this compound is going to be SN for tin, O. SNO, or snow. All right, and that brings us to our section review slide. So far, we have observed what the, a good approach kind of consistently for not only determining what the charges on our ions are, but once they start coming together, what is the chemical formula going to be? What is that ionic formula? And what do we name it? How do we call it? Or what do we call it? Excuse me. It's the end of a long day. All right, so our Lewis dot symbols, we haven't explicitly discussed, but this really has to do with the valence electron configuration of our metals and nonmetals as the ionic compounds are coming together. We'll be talking in more detail about Lewis dot symbols, though, in the next part of the lecture. But the valence electron configurations can be used to figure out what the charges on our ions are, and that's really what these example problems pertain to. As well as naming ions and ionic compounds. This set of example problems is much closer to like that last problem we just worked through, getting some good practice naming the formula as well as writing out the explicit empirical formula. All right, well, if you have any homework, be sure to double check and do your homework. But until next time, when we talk about molecules, class is dismissed.